Tum tum dee dum, dem tum dee dum, dem tum torum, tum tim tum torum.
Hello guys, my name is Aurelinse Gwenayir Sharoring, and I'm gonna share summary of presentation of Professor Prasad Kaparaju in IconSmart 2023 International Conference on Natural Sciences Mathematics Application Research Technology. And the presentation is about feasibility of biogas production from sugar industry waste. Certainly, we can delve into the detailed analysis of substrate requirement from our experimental data. Depending on the quantity of material introduced, variation in methanol content per cubic meter of methane per ton of fresh material become evident. The highest methanol content is observed in evaporated sugar syrup, signifying its rich sugar content, which implies significant potential. Let's further explore the characteristics of lignocellulosic materials. These materials form a lignocellulosic matrix, facilitating bacterial access to organic material. However, the accessibility of this matrix can be constrained by recurrent materials. Leveraging these assessments of methane potential, we can determine feasibility. But what does feasibility entail in this context? It involved an examination of viable technologies and diverse usage scenarios for biogas. For instance, you might be interested in biogas production for heat and electricity within a combined heat and power plant or CHP. Alternatively, you can opt for biogas upgrading to biomethane, which closely matches the quality of natural gas. Let's dive deeper into the scenarios, starting with scenario 1 involving CHP. In this scenario, biogas takes center stage, serving as the source for both electricity generation and grid supply. As a result, you'll witness the production of electricity, digestate, and biogas. What's particularly noteworthy here is that the biogas plant operates independently of grid electricity, making it self-sustaining. Moving on to scenario 2, we introduce the concept of CHP plus bio-CNG or biogas upgraded and compressed to meet natural gas quality, which finds its purpose as a vehicle fuel. In this configuration, biogas production follows a specific breakdown with 30% allocated to electricity generation and substantial 70% dedicated to biogas upgrading. This dynamic yields a multifaceted range of outputs encompassing electricity, bio-CNG, bio-CO2, and digestate. And yes, you guessed it right. Grid electricity remains entirely redundant in this scenario as well. Scenario 3 takes us further into the realm of possibilities by considering the incorporation of CHP plus bio-RNG, or biogas upgraded to renewable natural gas and injected into the gas grid. Remarkably, the outcomes achieved in this scenario closely resemble those of scenario 2, encompassing comparable plant outputs and overall results. So, in essence, these scenarios not only showcase the versatility of biogas utilization but also underscore the remarkable self-sufficiency achieved by the system, eliminating the need for grid electricity in the process. Now, let's scrutinize the procedural aspects. It all begins with sugarcane biogas, sugarcane meal mood, and co-degustation involving chicken manure. Both sugarcane biogas and meal mood undergo pre-treatment to reduce particle size, with steam pre-treatment enhancing cellulose and hemicellulose solarization, thereby enhancing the materials. These treated materials are mixed with chicken manure and introduced into the biogas. Within the biogas reactor, gas production takes place and subsequently stored. This gas can be channeled into the three aforementioned scenarios, enabling use within a combined heat and power plant for the generation of electricity and heat, or subjecting it to biogas upgrading to yield various biogas variants. The residual material derived from the biogas plant is reverted to as digestate, retaining its nutrient richness due to effective conservation. Remarkably, this digestate can be reintroduced into the sugarcane cultivation, underscoring an environmentally sustainable approach. In this manner, carbon is harnessed as a renewable gas, and nutrients are preserved and repurposed as organic fertilizer, thereby ensuring self-sufficiency in energy. From an engineering perspective, meticulous calculation consider daily feedstock quantities, biogas plant dimension, and comprehensive mass and energy balance assessments. Breaking it down, you will typically supply approximately 151 tons of feedstock daily, comprising roughly 82 tons of meal meat, 55 tons of sugarcane bagasse, and 14 tons of chicken manure. Additionally, the addition of water is necessary to ensure that the solid content remains below 10%. These materials are then introduced into three biogas reactors, each boasting a capacity of approximately 6,000 cubic meters. The generated biogas is subsequently directed into a storage tank. From there, it supplies a combined heat power plant, with the electricity produced being integrated into the digestate. This digestate material can be separated into solid and liquid fractions, with the liquid portion being returned to the front of the biogas plant for incoming feed. Upon closer examination, it becomes apparent that the biogas undergoes upgrading and is employed as compressed natural gas, or CNG, for vehicular application. However, a small combined power plant is deemed necessary to meet the energy demands of the entire operation. Consequently, a portion of the biogas is allocated to power the biogas plant, while the remaining biogas is earmarked for biomethane production. This biomethane can serve as a vehicle fuel or be injected into the grid. Additionally, carbon dioxide is present in the biogas, referred to as bio-CO2, which can be harnessed for various applications, including greenhouse gas management. Hello guys, so this is behind the scene. I made the voiceover for the animation. Organization and sharing, and I'm going to share the summary of presentation of Professor Prasad Kaparaju in ICON Smart 2023 International Conference on Natural Science Mathematics, Application Research Technology. And the presentation is about feasibility of biogas pollution from sugar waste industry waste. Certainly, we can delve into the detail of analysis of substrate requirements from our experimental data. Depending on the quantity of material introduced, variation in methanol content per cubic of methane per ton of first material become evident. The highest methanol content is observed in evaporated sugar syrup, signifying its rich sugar content, which implies significant potential. Let's further explore the characteristic of lignocellulosic materials. These materials form lignocellulosic matrix, facilitating material access to organic material. However, the accessibility of these materials can be constrained by recurrent materials. Differentiating this assessment of methane potential, we can determine feasibility. But what does feasibility entail in this context? It involves an examination of viable technologies and diverse usage scenarios for biogas. For instance, you might be interested in biogas production for heat and electricity within combined heat and power plant or CHP. Alternatively, you can opt for biogas upgrading to biomethane, which closely matches the quality of natural gas. Let's dive deeper into the scenarios, starting with scenario 1 involving CHP. In scenario, biogas takes sector, serving as a source for electricity generation and grid supply. As a result, you'll witness production of electricity, distinct state, and biogas. What's particularly noteworthy here is that the biogas plant operates independently of grid electricity, making it self-sustaining. Moving on to scenario 2, we introduce the concept of CHP and plus bio-CNG, which find its purpose as a vehicle fuel. In its configuration, biogas production follows a specific breakdown with 30% allocated to electricity generation and substantial 70% dedicated to biogas upgrading. This then yields a multifaceted range of outputs encompassing electricity, bio-CNG, bio-CO2, and biogas. And yes, you guessed it right, with electricity remains entirely redundant in this scenario as well. Scenario 3 takes us further into the realm of possibilities by considering the incorporation of CHP plus bio-RNG. Remarkably, the outcomes achieved in this scenario closely resemble those of scenario 2, encompassing comparable plant outputs and overall results. So, in essence, the scenario not only showcased the versatility of biogas utilization, but also underscored the remarkable self-sufficiency achieved by the system, eliminating the need for grid electricity in the process. Now, let's scrutinize the procedural aspects. It all begins with sugarcane biogas, sugarcane milk, and communication involving chicken manure. Both sugarcane biogas and milk undergo pre-treatment to reduce particle size, which steam pre-treatment and hashing cellulose and hemicellulose solarization, thereby enriching the materials. These treated materials are mixed with chicken manure and introduced into the biogas reactor. Within the biogas reactor, gas production takes us and is subsequently stored. This gas can be channeled into the three aforementioned scenarios and then used within a combined heat and power plant for the generation of electricity and heat or substituting it to biogas upgrading to the various biogas variants. The residual material derived from the biogas plant is referred to as the biogas, retaining its nutrient richness due to effective conservation. Remarkably, this biogas can be reconstructed into sugarcane cultivation, underscoring the environmentally sustainable approach. In this manner, carbon is harnessed as a renewable gas, and nutrients are preserved and repurposed as organic fertilizer, thereby ensuring self-sufficiency in energy. From an engineering perspective, meticulous calculation consider daily feedstock quantities, biogas plant dimensions, and comprehensive mass and energy balance assessments. Break it down, you would typically supply approximately 151 tons of feedstock daily, comprising roughly 82 tons of milk, 55 tons of sugarcane biogas, and 14 tons of chicken manure. Additionally, the addition of water is necessary to ensure that the solid content remains below 10%. These materials are then introduced into three biogas reactor, each boasting a capacity of approximately 6,000 cubic meters. The generate biogas is subsequently diverted into a storage tank. From there, it's supplied to combined heat and power plant, with the electricity produced being integrated into this state. This state material can be separated into solid and liquid fractions, with the liquid portion being returned to the front of biogas plant for incoming feed. Upon closer examination, it becomes apparent that biogas undergoes upgrading and is small employed as a compressed natural gas for vehicular application. However, a small compact power plant is deemed necessary to meet the energy demands of the entire operation. Consequently, a portion of the biogas is allocated to power the biogas plant, while the remaining biogas is earmarked for biomethane production. This biomethane can serve as a vehicle fuel or be injected into the grid. Additionally, carbon dioxide is present in the biogas, referred to as bio-CO2, which can be harnessed for various applications, including greenhouse gas management. Okay, it's done.